Welcome to today's class on real analysis. Today we discuss family of sets, their union and intersection. So first we discuss what is meant by a family of sets. Let A and omega be sets, and suppose that with each element alpha of A there is an associated subset of omega which we denote by E alpha. The set whose elements are sets E alpha will be denoted by set E alpha. So instead of speaking set of sets, we shall sometimes speak of a collection of sets or a family of sets. Now we define union of sets. The union of sets E alpha is defined to be the set S such that X belongs to S if and only if X belongs to E alpha for at least one alpha in A. We use the notation S is equal to union alpha belongs to A E alpha. Remark, if A consists of the integers 1, 2, etc. n, we usually use the notation S is equal to union M equal to 1 to n em, or S equal to E1 union E2 union etc. union En. If A is a set of positive integers, the usual notation is S is equal to union M equal to 1 to infinity em. In the above notation, infinity merely indicates that the union of countable collection of sets is taken and should not be confused with the extended real numbers plus infinity and minus infinity. Now we define intersection of sets. The intersection of sets E alpha is defined to be the set P such that X belongs to P if and only if X belongs to E alpha for every alpha in A. We use the notation P is equal to intersection alpha belongs to A E alpha. Now if A consists of the integers 1, 2, etc. n, we use the notation P equal to intersection M is equal to 1 to n em, or even intersection E2 intersection etc. intersection En. So it is a finite intersection. If A is the set of all positive integers, the usual notation is P is equal to intersection M equal to 1 to infinity Em. Here also Em is not extended real number. It just represents that it is a countable collection of integers. If A intersection B is not empty, we say that A and B intersect, otherwise they are disjoint. Now we give an example. If A is the set of real numbers x such that 0 less than x less than or equal to 1, for every x in A, let Ex be the set of real numbers y such that 0 less than y less than x, then 1. Ex is contained in Ez if and only if 0 less than x less than or equal to z less than or equal to 1, and 2. Union x belongs to A Ex is equal to E1. 3. Intersection x belongs to A Ex is empty. So we'll do this problem. So solution. First we understand what are these sets. We have A is set for x in R such that 0 less than x less than or equal to 1, and you can see that this is nothing but the interval 0 1. So you have this is 0 and this is 1. So closed at 1, open at 0. So this is your set A. So that is A is actually equal to 0 1, and by definition Ex is set for y in R such that 0 less than y less than x. So this is actually equal to, suppose that this is 0 and this is 1. So if you consider an x here, so this interval is Ex. And we have x can be maximum 1 because 0 less than or equal to x less than or equal to 1. So E1 is set of all y in R such that 0 less than y less than 1. So this is actually equal to open interval 0 1. Now you consider 1, how Ex is contained in Ez if and only if 0x is contained in 0 set. So you have this 0 x. So this interval, and 0 set. So this interval. So this interval is Ex, and this interval is E set. So from this you can see that, so this implies 0 less than x can be less than or equal to set, and you know maximum value of set is 1. So this is less than or equal to 1 by the definition, since set belongs to A, set can be less than or equal to 1 if and only if. That is, Ex is contained in Ez if and only if 0 less than x less than or equal to z less than or equal to 1. Now we prove that union x belongs to A, Ex is equal to E1. We have for 0 less than x less than or equal to 1, Ex is contained in E1. Therefore, union x belongs to A, Ex is contained in E1. This is 1. On the other hand, we have E1 is contained in the union x belongs to A, Ex, by definition of union 2. So from 1 and 2 we have union x belongs to A, Ex equal to E1. Now we prove that intersection x belongs to A, Ex is empty. By definition we have y belongs to intersection x belongs to A, Ex if and only if y belongs to Ex for every x in A. But here, for every y greater than 0, y does not belong to Ex if x is less than y. Hence, y does not belong to intersection x belongs to A, Ex. Therefore, intersection x belongs to A, Ex is empty. Now we discuss some remarks. 1. A union B equal to B union A. You know this property is known as commutative property. You can prove this. Let x belongs to A union B. So this implies x belongs to A or x belongs to B. So this implies x belongs to B or x belongs to A. So this implies x belongs to B union A. That is, A union B is contained in B union A. And if you let x belongs to B union A, we have x belongs to B or x belongs to A. So this implies x belongs to A or x belongs to B. So this implies x belongs to A union B. This implies B union A is contained in A union B. So if you take this as 1, this as 2, we get from 1 and 2 A union B equal to B union A. Now 2, A intersection B equal to B intersection A. So x belongs to A intersection B implies x belongs to A and x belongs to B. So this implies x belongs to B and x belongs to A. So So this implies X belongs to B intersection A. So this implies A intersection B is contained in B intersection A. We take this as 3. And X belongs to B intersection A implies X belongs to B and X belongs to A. So this implies X belongs to A and X belongs to B. So this implies X belongs to A intersection B. So this implies B intersection A is contained in A intersection B. So this is 4. So from 3 and 4, A intersection B equal to B intersection A. Now by similar arguments you can prove that A union B union C equal to A union B union C and A intersection B intersection C equal to A intersection B intersection C. These properties are known as associative properties. And you do this as a homework, proof of this. Now you can do the distributive property, like how A intersection B union C equal to A intersection B union A intersection C. So this is the distributive property. We let, so to prove this, E equal to A intersection B union C and F equal to A intersection B union A intersection C. Let X belongs to E. So this implies X belongs to A and X belongs to B or X belongs to C. So this implies X belongs to A and X belongs to B or X belongs to A and X belongs to C. So this implies X belongs to A intersection B union A intersection C. Therefore, A intersection B union C is contained in A intersection B union A intersection C. So you take this as A. So let X belongs to A intersection B union A intersection C. So this implies X belongs to A intersection B or X belongs to A intersection C. So this implies X belongs to A and X belongs to B or X belongs to A and X belongs to C. So this implies X belongs to A and X belongs to B or X belongs to C. So this implies X belongs to A intersection B union C. So therefore, A intersection B union A intersection C is contained in A intersection B union C. So take this as B. So from A and B, we have A intersection B union C equal to A intersection B union A intersection C. 1. A is contained in A union B. And second remark is A intersection B is contained in A. And the third remark, if A is a subset of B, then A union B is B and A intersection B is A. As you know, fourth one, if 0 denotes empty set, then A union empty set is A and A intersection empty set is empty set. You can use phi as the notation for empty set, no problem. So that's all for today. Have a nice day.